Thank you. So anyway, we will be revisiting some of this in the when we go to the SSA part. So um, um, uh, um, so now let us go to the region of domination and the loops. And that's what is of interest to us, especially in picking up things for analysis purposes. So a region of a node which dominates a set of nodes, um, it's typically defined as the header which dominates all the nodes, and in that particular region. So for example, 1 dominates 2 and 3, for example, and that would be forming a region of domination. And all the edges in between are also included in the region of domination. And um, um, we are interested in a special region, which is loop, which is what we call as a strongly connected component of this. What it means is there is a path from each node to every other node in this particular graph. So graph is obviously a collection of nodes. What is a strongly connected component of a graph? In the directed sense, if we pick any two nodes in it in an ordered pair, A and B, we'll always be able to go from A to B by following directed edges. So that is the strongly connected component. And obviously, our loop is a strongly connected component. And this is single entry, as I was mentioning. And the back edges of the loop are what are really defining this particular sorry about that, this particular region. So now let us find this particular loop which we had sort of seen earlier in terms of how to go about finding it. And so they are all defined because of the back edges, and this is also called as the natural loop of the graph. That's because these result out of the constructs of the programming languages, such as for loops, while loops, etc. Naturally, they result in such control structures without programmer doing go-tos and all these things. That's why they are also called as natural loops, but the better name for them is single entry, because they do have this property of a well-defined entry point through which you always go, and you then iterate in that region, and then you exit. And therefore, you cannot enter this region, whatever is shown here, this white region, except you must go through this header edge. Typically, in a given loop, there is also something called as a pre-header, which is right before this A, and in that there is some loop initialization or iteration code, which we had seen this example when we did the basic block generation some time back. The pre-header contains the initialization of the loop iteration variables, etc. And we typically enter that first, then we enter the header, and then we reiterate through the header, evaluating these conditions, whether the loop is terminating or not. And if the condition is true, we exit. So the check for termination may or may not be there in the header. Sometimes it is there, like in while loops, for example. However, in repeat until loops, typically it could be at the tail, at the level of B. There could be also breaks in between the body of the loop, which exit the control statements in the loop, etc. And so there could be exits anywhere within the body of the loop. So so what exactly is this natural loop or single entry loop is we are interested in finding out here all the nodes which are defined by this backage. What is really a backage? A backage is going from a given node which is dominated by another node back to that dominated node. So A is dominating B here, and there is a directed edge from B, the one which is dominated, towards the one which is dominating, which is A. And each one of them defines this particular loop, because that's how the control goes back and again iterates on a forward path through one of the edges. On a backward path, it goes through this particular edge, and the control simply cannot enter this region unless it comes through A. So the body of the loop is, or the loop itself is defined therefore as the entrance, which is A, and the backage, which is B. So those two nodes are there. And in addition, all the nodes which can reach B without going through A. So this is an important part here. So the control is therefore flowing forward through the body of the loop towards B without going through A. Why is that? Because there could be another loop there which maybe brings the control back to A through another backage, and we'll find that as a part of that particular loop. So here we are interested in the forward part of it. For this particular backage, we're interested in finding out what all the nodes that carry the control forward from A towards B, as simple as that. And so we want to enumerate that in the acyclic sense of the paths, not the cyclic ones. And what we will do, therefore, is therefore collect all these nodes which are bringing the control forward from A towards B. So one way to find the natural loop is find, of course, the backage. So we have these DOM relations, which we have seen. And then I want to find out if I'm forming a loop with somebody whom is dominating me. So how do I check that? Well, I go through the list of all the nodes which dominate me, and I find out if I have a directed edge to one of them. If I have an edge to one of them, then that is the backage, and that will form a loop. If I have edges to multiple of them, they will all form different loops, and I will try to take up each one of them and enumerate them as the loop. If, of course, I don't have any backage, then of course I do not form a loop because of lack of backage. So let us say we looked at all the nodes that are dominating me, and I found a backage, directed edge to the dominator. And so now there are two types of algorithms which exist. What I will maybe first find out is all the nodes that are dominated by A. I will enumerate those. I'll find those out first. Remember, this is a reverse relation in the sense, so far I have been, through my dominator algorithm, I have been finding out all the nodes that dominate me. But I don't have any relation as such who all dominates A. Okay. Now that is found by this dominator tree that we looked at. Because if you look at this dominator tree, let's go forward again a little bit and see what all it's showing is which are the nodes which are dominated by a given node. So for example, look at this dominator tree rooted at 4. So 4 is dominating 5, 6, 7. 7 is in turn dominating 8. So in short, 4 is also dominating 8. 4 is dominating 9, 4 is dominating 10, all these kinds of stuff is there. So if I want to find out who all 4 is dominating, I will have to take all this tree which is rooted at 4. And using that, then I can try and find out all the nodes which are dominated by 4. So in that sense, dominator tree is constructed as a indirect step before this particular version of the algorithm, which is first finding the back edge. For finding the back edge, we don't need dominator tree, of course, because all I need to find out is if I have to find out the back edge from B, I will just look at the DOM set of B, which tells me which are the nodes which are dominating B, and then just examine if I have an edge to any one of them. So that step is independent of dominator tree, but the next step, that is to find the nodes which are dominated by A, I need dominator tree, because just by looking at the DOM sets, who all is dominating me, that is not clear in terms of, it's a reverse relation to that. So I must find that using dominator tree. So remember here, again, the dominator tree will be needed for number 2. Then look at, then out of those nodes which are dominated by A, I will then check the nodes that can reach B, which are dominated by A. Why is this important? This is important because we want to find out all the nodes that bring control to B in the forward sense, and we don't want to have those nodes which are dominated by A but which may not bring control towards B. So imagine here there is an exit of this loop, and that is going to some node C here, and from that C I don't have any path towards B. Okay, it doesn't reach B unless and until it might go all the way back through A and then reach this B through another path. That's different, and that is why I want to see if there is any path from this C towards B which doesn't go through A. So in that case, I don't find such a path C from C to B, and therefore C is not really part of this loop. However, C is actually at the exit of this loop, because what is going on here is the control will somehow come into A, go through one of these nodes, which is in the white, and so on, through one of the paths which are dominated by A, and which keep proceeding further towards B. Finally, the control reaches B, and then from B, it again iterates back along this back edge to A, and it will keep moving in this particular area. And at one point, when the condition becomes false, etc., the control will leave this region through this exit edge, which is going towards this C. From this C, there is no other way to come back into this loop except to re-enter via this A. And that's why all the nodes which are dominated by A, but which do not have a path towards B without going through A, are not included in the loop. So for doing this, we need to find out what is the path from this node which is dominated by this A, and whether that path is there without going through A towards B, and where there exists some path which is like that. And for that particular reason, we need a dominator tree as well in the step number 2. So this is one way to find this particular loop, but you can see here that we need to construct this dominator tree, and this will be a indirect way of checking nodes. If the loop has multiple exits, what will end up happening is we'll have a large number of such nodes which do not really belong to the loop, but to which we'll have to keep checking if they have any path towards B. So a better way would be to start with some nodes which already have a path to B, and then keep moving backwards and stop when we reach this particular A. Now, why is this particular procedure better? First of all, because of this reason, that it will not deal with all these nodes which are on the exit of this loop, because they won't have a direct path to B. So if we keep moving backward along B's predecessors and their predecessors and so on, they will never reach such C's which are in the loop exits. So we'll avoid visiting them. Second is we'll enumerate all the nodes by going through their predecessors, and they will be guaranteed to be dominated by A. The reason is B is dominated by A. So as per the definition of dominators, as you can see, if one of the predecessors or their predecessors and so on in a transitive sense is not dominated by A, then A cannot be dominating B. But we have already checked in this case that A is dominating B. So all the predecessors and their predecessors and so on must be dominated by A. So that number 2 check is automatically achieved here in this particular algorithm. We don't have to explicitly check it. We don't need the dominator tree or forward dominator relation. The fact that we are starting with B and B is dominated by A, and we are moving backwards from the predecessors of B and their predecessors and so on, guarantees that all those nodes must be already dominated by A. We don't have to have any further check on that because of the way the dominator relationship is. And so we keep collecting them, and they are already also guaranteed to have a path towards B, because we have started going backward in the predecessor relationship sense. And so we don't have to check that condition also, whether they reach B or not. So if we keep adding them and then pushing them into the loop and putting them, the predecessor which is not visited yet, if we put them in the list of next set of nodes to visit, we can take up first the predecessors of B. In the second round, we can take up the nodes which are at level 2 in terms of being predecessors of B. So not the immediate predecessor, but their predecessors. And we can keep adding more and more. And if we somehow find that A is one of the predecessors, we will not add that, because obviously we have, that means that particular path has been already explored. And this way, by going backwards, we would explore all the paths, and the termination will be that we are not able to add any more predecessor because we already reached along that path to A. So that is the preferred algorithm. Again, how will that work? The first step is the same here, backage. The second step start with B and take its predecessor and see if it is already in the loop or not. If not, then add it and then put it on the list which is to be visited. And if the predecessor, however, is A, then that basically means that we have reached along that path towards the dominator node, and we don't need to keep moving past that. In other cases, we will keep adding the predecessor to the loop and putting it on the exploration again on the queue, and we'll then take it out of the queue and again start the exploration going backwards, adding again to the loop and so on. And that way we'll enumerate the whole set of nodes which are reachable to B, but which are dominated by A. And we will exclude all the nodes which are dominated by A, but which are not reachable to B, because we have, of course, gone backwards from B. And we will exclude all the loop exits. So the collection of all these nodes and all the edges which connects them forms the loop, in short. So we can do some small example here, and I will leave the rest of them for you to study again. So we'll do this 9 and 1, which is a big loop here. First of all, we had a dominator set of 9, and that contains obviously 1. and many other nodes like 7, 8, I believe, and 3, 4 maybe. And we check if there's an edge. So obviously 9 does not have any edges to the dominators except to the 1, and so we pick this particular edge, and now we want to enumerate the loop of this. So we can start going back from 9 and add this to the loop, again following the same exact algorithm, and adding it to the queue as well, and then keep going backwards from those nodes by adding their predecessors, and in a transitive sense reach all the way back to 1. So as you can imagine here, we have the whole graph here, because then I leave it to you to work out the steps. From 9, first of all, we'll add the predecessor 8, and from 8, we'll add the predecessor which is 7, which then will the predecessor of 7, you can see that will get added as 10, and all kinds of things will get added here. So don't, of course, visually look at it because that's confusing. It is basically all these paths. So some of them might be cyclic paths, but they're not cyclic with regard to 1. That is the most important thing here. So 7, 8, 9, you can see that will get added because of cyclicity, etc. But that doesn't matter. That means that particular region which is leading from 1 towards 9 goes through some cycle, and that's perfectly fine. It will pick up cycles as well as acyclic regions. Once you go through this, go to the predecessor. If it is not currently in the loop, then add it, put it in the queue, and for exploration further. If it's already in the loop, then there's no need to explore it again or add it for exploration, because it must have been gotten added, and its predecessors would therefore get explored. So following this simple strategy, it will enumerate. Once it goes to 7, it will take its predecessors, which are all the incoming edges. As I said, 10 and 5 and 6 will also get added there. And when 10 is processed, for example, it will again come back to 8, but 8 was already explored and added to the loop. So it will not add 8 again, because otherwise it will be going in circles, and it would have explored eventually by adding only those which were not in the loop and then processing their predecessors. It will keep moving backwards, and eventually things will not get added more, because once you reach 3, for example, its predecessors, which are 1 and 2, will get sort of process next when we are processing 3. 1 is already there because it's a part of the loop, so we will not explore the path which is from 1 to 3 backwards. But we'll go to 2, of course. We'll add 2 there. And another node which is the predecessor of 3 would be 8. Now 8 is already processed, as you can see here. That's another loop there. And so 8 will not get added again and will not get explored again. So it will cut out 3 to 1 path. It will cut out 8 to 3 path, but it will explore the path from 2 to 3. Very interesting algorithm. And it will add 2. And then now it has gone to 2, and then you can see that it will take 2's predecessor, which is only 1. It's already there in the loop. It will not add anything at this particular point. Everything is completely done. There is nothing more to be explored. The queue is empty, and therefore the collection of all these nodes, all of them from 1 through 10 will be a loop, and all the edges in between them will also be loop. And that's why this whole thing will be marked as a loop. Any questions about this? So it's a nice simple algorithm. This is the one which is typically implemented because it doesn't need dominator trees. And it just starts with a back edge, starts with the head of the back edge, which is 10 here in this case, takes their predecessors and keeps exploring, going towards the dominator, and in that process it will add everything here. So try to play with this examples and see your answers. In this case, 10 to 7 is a back edge, so it will go toward the predecessor of 10, which is 8, and things like that. And you will see some interesting results here. So this one is probably pretty obvious. This one might be a little interesting because of the predecessors of 7. You can see here that I think 7, 8, 9 will probably, 7, 8, 10 will get added to this. So yeah, as I mentioned, going backwards from 7, you can see that 7 has 3 predecessors. 5, 6, and 10, they will get added because again they are on the path from 4 to 7 without going through 4 again. Okay, so we'll again follow the algorithm. We'll detect the back edge because 4 is dominating 7. And now we'll take 7's predecessors, which are 5, 6, and 10, and we'll add them to the loop. And then we'll explore their predecessors. So note that we are now exploring 5, 6, and 10. 5 and 6 are easy because further in the next step, if we go to their predecessors, 5's predecessor is 4. 4 is already in the loop, so no more exploration there. That's done. Similarly, 6 predecessor is 4. It's already there. We don't need to add anything more there. Those paths are already explored. But now come to 10. 10's predecessor will be 8. And so 8 will get added. And now to the loop. And now 8's predecessor has to be explored. 8's predecessor will be 7. And of course, 7 is also there already in the loop. We started the loop by putting both parts of the back edge into the loop. And so 7 is there. So no more exploration there, but 8 would have gotten added. And now, so therefore, the loop is 4 and 7, the part of the back edge. 5 and 6, which got added, going through the predecessors of 7. 10, which is again as a predecessor of 7. And 10's predecessor, 8, also got added. So now, and no more things are getting added. So this is the loop for 7, 4. Now you can see that this loop is very interesting. The control is coming forward from 4 to 7 along this 5, 6, and so on. And is also kind of circling around 7 without going through 4. And then it goes through back to 4 by following the back edge. And in that process, you can see that another loop is being sort of covered there, 7, 8, 9, 7, 8, 10, I'm sorry. And then this control comes back. So it is picking up some loops which are sort of now getting generated as a part of the other loops here. So this is a question of, you can see that 7, 4 loops kind of subsumes 10, 7 loop here. And so you can think of that as a inner loop of 7, 4, which is formed in the control sense, and that is actually true. Um, now, sometimes, of course, you will also see that there could be two loops which might share a header, which may have certain parts overlapped, but which may have two different sort of back edges. So it is possible that some loops are also sharing certain edges. So in that case, what is going on is you are traversing. So for example, if there were a loop, remove for example this edge from 10 to 7, and imagine some other loop which was let's say going back straight to 1. So what will happen here is the control will come forward here from 7, 8, and it will branch in two different ways. It will go like this to 9 and maybe form a loop, or maybe it will go to 10 and it might form a loop back to 1. Now you can see that there are two different loops which are sitting there, and it's possible that they share some parts of their bodies, and but they're not perfectly nested. It's possible that maybe only one loop will keep executing here, then it will exit this loop. As far as the other loop is concerned, which is going from 10, there would be exit, it will enter this loop and go back there, and vice versa. So in such cases, you cannot proclaim that one is nested within the other, but in this particular case, you can. So loops could certain bodies and maybe rooted at the same header, but they are two different loops. They are disjointed in the sense at least some node is there in one which is not in the other, and therefore one cannot transform them as nested loops, whereas in many other cases you will have the nested loops which are generated here. So now you may ask me, so is it go-to oriented effect? The answer to that is not necessarily. It is all an effect of the breaks statements, and some of them could be labeled breaks that you can break out of this loop and go into that loop, and then terminate a loop in a particular way, or if you have some constructs which allow you to just skip a whole bunch of statements in a given loop and go to a particular node, such as continue statements, and from there carry out some jump, which is break out of that particular loop and go to the other label in the outer loop, and then continue from there. Those could lead to such loops. But our goal will be to anyway enumerate them separately and deal with them in the transformation. Maybe there is some code which is sitting in 9 which we want to move out of this other loop. We could very well do the transformation, or there is some code sitting in 10 which could be moved out of this other loop, and that could very well be done again by the transformation, because the essence is this, that anything that is touched, if it is touched in a loop, could iterate thousands or millions of times, and moving them out safely out of the loop would make sense. If it's of course a nested loop, then what we will try to do is we'll try to move things out of inner loop first, such as 7, 8, 9, 7, 8, 10, and once we move it out of that, we will create a pre-header to 7, and then it will be a part of the outer loop, which is this big 7-4 loop, and then we'll try to move it out of from there to creating a pre-header to 4 some statements, and that way we'll successively move it into outer and outer loops. So when they are nested, it gives a very systematic method. If they are not nested, then we just treat them individually and try to do the optimization based on what is going on in the common or uncommon parts of the loop. And any questions about this? And we will deal with especially loop transformations in terms of the data flow, which is called as Loop invariant code motion is one of the big transformations. What it means is imagine a statement sitting inside a loop and such as a is equal to 10. Okay, variable a is equal to 10, and is assigning the same value to a again and again and again inside the loop, and is executing millions of times. So what is the point? So what the compiler will try to do is first identify this loop, then identify the fact that a is invariant, that is a's value is not changing, and then we'll find out if it could be moved out of this particular loop, creating a pre-header out of maybe one or whatever loop it is involved in. If it's in the innermost loop, we'll try to move it out of that first in the sense of nested loops, then go from the nested loop to the next outer loop and so on. A lot of these are reducing the execution time of the loop, and that's why loops are really significant in terms of detection here. Any questions about detection of loops, inner loops, outer loops, nested loops, whatever, the method of detection, etc.? Okay, and you can of course come back and ask me in the office hours. So try to step through the remaining and generate these loops. So dominated tree, as I said, was one of the implicit steps if we follow the algorithm, the one which is given in the slides, to construct the loops. So loops were one type of region. The other kind of region could be simply a cyclic region, the idea there is of course, the header will dominate the nodes which are inside. So if you just look at this region here, just 1 and 2 and 3, you can see that 1 dominates 2 and 3. Of course, 2 does not dominate 3. So a region which is formed by by 1 with regard to 2 and 3, that's an acyclic region. What it means is the control must come via 1 into either 2 or 3, and we can do certain interesting things here just by noting such acyclic regions. Whether or not they form a loop is a totally different condition. So let's just ignore the fact that they're inside some kind of loop. Forget that part for now. But if you just focus on 1, 2, and 3, so let's say there is some operation here in 1 which is feeding its value to 2 or to 3. You can see that that operation must execute before the feeding of that value to 2 or to 3 occurs, and that is why this particular type of region is also called as extended basic block. In other words, the operation there will occur first, then whatever nodes are dominated by that parent basic block, they will execute, and so on. So that operation can be safely assumed to take place always before the other operations in the dominated nodes, and because of which we can go top down and we can go to the root node like this one, find out what is going on to the temporary or to the name in terms of constant. For example, if the a is assigned as a constant 10 here and a is used in 2, the question is it safe to replace the use of a in 2 by the constant definition in 1? The answer is obviously it's always safe, because no matter what happens, you cannot come to 2 without going via 1, and which basically means A is equal to 10 must occur here before you come to 2. And therefore, the value of A, which you see in 2, is always constant 10, which is assigned in basic block 1. So you can do this type of stuff in what is called as the extended basic block, the propagation of constants, etc., without incurring any additional analysis. And that's why this detection of these acyclic regions is also very useful. Similarly, from 4 to 5, 6, 7, if you assign some constant in 4, let's say variable B is given some value 20. And B is used in 5 and 6 or 7. What value of B do you see? The value will be always seen coming from top as whatever was given to B, which is like 50, will be seen in 5, 6, and 7, and you can replace it doing constant propagation. If there is no other value, of course, defined. If there is another value defined, then things will be complicated. We'll have to find out order in which it will came and so on. And that is something which is a topic of SSA, which will deal with the second assignment if it is there. But if there is no second assignment in a acyclic region, the one which is coming from the dominator, which is the root, is the one which prevails. And that's basically accounted by finding this region, which is a acyclic region, which is what we call as extended basic block. So cyclic regions, loops, very important for moving operations. Acyclic ones, simplicity of propagation of facts. Both are regions, and they are all found through this dominator and back edges and so on. Before we move now towards data flow, are there any questions about control flow and so on? Okay, so now one of the things that we use this also all these graphs and whatever we have found, control flow graph. We could take the control flow graph, which has an IR embedded in it, etc., and we can analyze it. And for bettering the analysis in terms of the timing, etc., what we can do is we can organize it by using the relationships that we have found. In other words, you can see here that we can start a data flow analysis or do some analysis in the basic block, as I said earlier, and then propagate its result to 2 and 3 based on this dominator tree. From there, maybe we can iterate and find out the results of the data flow analysis for this very small loop between 3 and 4, generate some results of data flow analysis, and we keep going down and down and down, again in the topological order. If we do that, it will save us tremendous amount of time. We can do that by finding these regions and organizing these cyclic and acyclic regions. Both we can find the loops and other things, and we can simply organize the whole thing going from top to bottom, and we can drive the analysis using this order from top to bottom, just like shown here by the dominator tree. It will tremendously speed it up if we do that, because we are propagating the facts in the once they stabilize in the forward sense, going from top to bottom. Or if we skip these steps of loop detection and region detection, can we simply stay with the vanilla control flow graph and organize the analysis on this and simply iterate and find results? The answer to that is absolutely yes. So what will be the flip side of this? So we have this control flow graph now, and we have all these different statements inside the control flow graph, which are IR statements. Remember, we haven't done any loop detection on this. We haven't done any acyclic regions detection on it. But we just have this IR, which is embedded and which is sitting inside the control flow graph that we have detected. And now what we want to do is we want to analyze this, get some data flow facts generated in terms of which values are carrying constants and which values are not carrying constants and things like 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 that. Go from one basic block to the other, propagate the facts, and randomly propagate these facts all over, just like we did for dominators. We'll just do this. We'll pick any basic block. We'll propagate the facts. We'll throw it back in the pool. We'll take another block. We'll propagate that across its boundaries, and we'll keep continuing this process. And finally, we'll find answers. If we do that, obviously, we will spend more time than if we do it in an organized way. So that is another reason to have the detection of loops, detection of acyclic regions, to be able to organize the data flow. So let us first answer the question, what is the data flow fact that we are trying to propagate and answer? And that will give us a very clear picture in terms of what this analysis really means. So as you can see in this simple graph, control flow graph, what is going on is the control starts at B1, and we have three statements there. I is equal to certain thing, which is called as D1 statement. J is equal to something, which is D2 statement. And A is equal to U1, which is the third assignment statement of the IR level. So we call these as definition points of the variables first, or what is called as a static definition point. So in short, at D1, the value I has gotten assigned some value. Okay. And I then carries that value from there downhill. So if you, for example, print I in D2, what value you will see? You'll see the value which is M minus 1. Okay. They'll be different at different execution times, depending on the value of M, etc. But they will always be seen as M minus 1 in some symbolic sense. Now this will keep happening. Let's say keep going. Whatever I value is carried, we'll keep following that. Next, we'll go through, after we execute B1, we'll go to B2, and we'll carry this value of I. Now again, which value of I we are talking about? The one which we started with, B minus, I is equal to M minus 1. So M minus 1 is what we are going to carry in the B2. We'll add 1 to it. We'll now have the value of I is equal to M. And from there, we'll carry that value of I from D4 onwards down. We'll carry the new value of I, which is M. So this tells us what is going on in terms of how the data is flowing. So the data is flowing or following the control arcs, and it's carrying with it simple definitions of the values. The first one coming out of D1 is being carried through, and the definitions are telling us which value is getting assigned where. So this is basically the static representation is telling us that a value is being transferred from one to the next point simply because of the flow of data coming from that particular statement, which is before to the current point. So there are two issues here. What is called as a control point, or where the data is generated and where it is propagated as per the control flow. So this is called as the points in the flow graph. So the point is in the flow graph could be between the statements, or before the first statement, or after the last statement. So you can see here that there's a point before D1, there's a point after D1, and um, so on. There's also a point after D3 here, which is before the control branch out. And so you can see that all these different points are possible in each basic block. The control flow dictates from where to where we can go, and depending on where to where we can go, the data will be carried by that particular name along that point. So the question is where all we can reach using control flow in this representation, which points we can reach, and that's why we have given you that particular reachability question. So the answer to this question about the number of points is B1 has 4 points. One is before D1, next is after D1, before the third one is after D2, and fourth one is after D3. So there are 4 points. B2, B3, B5 have 2 points. One is before each of the definitions, second is after. So each one of them have 2 points. And if you find out which values are carrying what at what points, we will immediately get a feel of how is the data flow in our representation. So as I said, this value, which is D1, is taken by the variable I as it flows through the B1. This goes down, and at B2, right before D4, if you examine I, it is still M-1, and that's the value you will see there. When you come down first time, when you come down through this iteration, D4 is going to D5 and so on, and again going back as the back arc. What is the value that you will see? You will see a different value. You will see the value of I is equal to M first time. Second time it will be M+1, etc., etc. So you will see, in short, D4 at the entrance of the block, B2, or you will see D1 as the value if it's coming first time. So depending on how you traverse at each point, you might see one of the 2 or one of the 3 values being brought in, and by knowing which values are come in where, we will be able to analyze what is going on with the data flow of the problem, and that is what we'll try to do. We'll place these statements, we'll find out if we can go from one point to the other. How do we find that out? There has to be a path, a reachable path. If there is a path, we'll go along that path, we'll carry that value. And if we can bring that value there through that path, that value will be delivered there. Depending on which values are delivered where, we'll find out whether those values are maybe all of them bind to the same constant or not. If they do, maybe we'll do some optimization like the constant propagation. If different values are coming in, like in this case, example of I, first is M-1, second time it's M, third time it's M+1. So obviously they're all different. They're not at all constants. They're variables, but they're also different. And so you won't be able to do that optimization for I. And that's the whole idea behind putting now the data flow on top of this control flow. So quickly summarizing, path is a sequence of these points, P1, P2, which go through the basic blocks and which are there as per the connectivity of these basic blocks with each other, etc. And the values of these which are brought as per the paths. And that's what I will stop today for. We'll formalize these values which originate, like I is equal to something as a definition, and then whenever I is being used here, we'll term that as a use, and we'll try to find out is which definitions are reaching which uses. And first we'll figure out the path. What this red um, thing is showing here is really there is a path from the beginning of B5 to the B6. How is that path? That path goes like this and then goes through these basic blocks and goes all the way over here. And that particular path we must optimize in terms of which values go where, etc. in case we want to transform the program, like constants or any other things that we want to influence. So in short, the control flow provides the paths along which the data flows, and the data is carried by these names of these variables. And some data is delivered here and some is delivered there. Some data that cannot get delivered because some new definition to that variable occurs and the old data is gone. Like for example, if this I were to be redefined as the next statement here in D2, the value of I will be immediately lost because it will not be a -1 anymore. It will be, let's say, n. If I were to be defined as n here, that value will be immediately gone after these statements. And so therefore, we will not be able to propagate the value of I and optimize it further in case we wanted to, because it will be smeared out by the next I. So let's look at all these definitions, uses, how it affects, which values go where, and what analysis is done to find out what we call as a reaching definition analysis. So we'll stop here for today, and thank you, and we'll see you in the office hours. Bye now.